So we're going to continue on with our study of radicals here and roots, as we are going to go from square roots and simplifying those into the idea of higher roots here. And so if we would talk about, for example, a cubed root, which you see there, the symbol for a cubed root has the root symbol with little 3 tucked into it. It says it is an operation that asks the question, what number times itself 3 times will give you that number. Similar to a square root. It's just now you need 3, a number times itself 3 times in order to get there. So basically our understanding needs to be that a root is the opposite of a power. And so if you think of a cubed root, it's saying what number cubed would get you there. Same thing with a fourth root. It's saying what number to the 4th power would get you there. And so on with a 5th root and a 6th root and so on. So let's go ahead and look at cubed roots here. And an example of simplifying a cubed root situation. So similarly to how we simplified square roots, using the factor tree method is going to make life easy for most of us, because most of us don't know our perfect cubes. And so by doing a factor tree, I get down to my prime factorization of 2, 3, 3, 3, 2. Now, because we're looking for a cubed root, I'm no longer looking for pairs, I'm looking for triples. I'm looking for a number times itself 3 times. So in this case, when you look at what we did to 108 here, and we did our factor tree, we're left with 3 3s and 2 2s. So therefore, the triples get to go outside, and the pairs and the lonely ones have to stay inside because we're looking for cubed roots. So therefore, the 2's both stay inside, making 4, and the 3 comes outside because a triple now comes outside and becomes 1 in front. Just like we did with a square root, but now we're looking for triples. So our next example here is going to be a large numbered 4th root, and we're going to put a variable in it. So if we have the 4th root of 6,480x to the 7th, we begin by doing our factor tree. Now hopefully all of you can look at 6,480 and know that 10 goes into that because it ends in a 0. So I get 10 times 648. I divided that by 4, making it 162 and 4, which is 81 and 2. Once you're there, now you're into more common numbers. We can simplify the 10 to 2 and 5, the 4 to 2 and 2. 81 is 9 and 9, which is 3 and 3 and 3 and 3. And we now look at our list here. I'm looking for a 4th root, so I need groups of 4. So I see 4 3's, I see 4 2's. So I can pull a 3 out front and a 2 out front, and I have this lonely 5. Anything that does not have a group of 4 is going to stay on the inside when we're finding 4th roots. So now, when I look at my answer here, I also have to consider my x's. My original problem had x to the 7th in it. And so if I write that out as 7x's, and again I'm looking for groups of 4, I have this one group of 4 and then 3 left over. So that group of 4 comes out front and becomes 1x, and we're left with x times x times x on the inside. So our final answer is going to be 3 times 2, which that gives us obviously our 6x. And on the inside of our root, we're going to be left with the 4th root of 5x to the 3rd. It is important that you write this 4th root up there because it is different than a square root. Alright, so there's one final thing to look at here, and that's going to be talking about signs with 3rd roots, 4th roots, and 5th roots. In our previous lesson, we looked at imaginary numbers, and we talked about how square roots of negatives are impossible, so we had to create imaginary numbers. But when we look at the difference between cubed roots and 4th roots, we need to look at that idea of a negative. A cubed root of a negative actually does exist. And the reason why that is, when you think again of the inverse or the reverse function, a cubed root is the opposite of x cubed. If you take a negative and you cube it, you're going to end up with a negative answer, because a negative times a negative is a positive, times another negative would bring us back to a negative. So therefore you can have a cubed root of a negative number. For example, 27 is a perfect cube. The cubed root of negative 27 is negative 3. However, a 4th root is going to have a 4th root of a negative number is going to end up being imaginary again. for that same reason. If you have 4 negatives multiplied together, you're going to get back to a positive. So the idea of taking roots with negatives, the big idea comes from odd and even numbered roots. If you have an odd numbered root, you can have a negative result without having to use imaginary numbers. If you have an even numbered root, a second, fourth, or sixth, or so on, you can take the root, but you're going to have an imaginary number if you have a negative in there. All right, good luck. If you have any questions, we'll talk about them on Monday.